On December 25, 2021, the $10 billion James Webb Space Telescope launched to peer deeper into the cosmos than ever before to find the universe's point of origin. Within 18 months, it detected galaxies from 325 million years after the Big Bang and mapped cosmic structures spanning billions of light years. But buried in the data lies a disturbing conclusion. The universe has no center. Not that we haven't found it, the concept itself is meaningless. JWST proved with 99.9% confidence that the Big Bang didn't happen at a point, but everywhere simultaneously. What if asking, where is the center, is like asking, what's north of the North Pole? A grammatically correct question with no answer. What if this isn't a technological limitation, but a revelation that challenges our most basic intuitions about reality itself? Today, we examine why the most powerful telescope ever built cannot and will never find the center of the universe, and why this impossibility tells us something far stranger about reality than any discovery possibly could. Prepare yourselves. We begin. The search for the cosmic center represents one of humanity's oldest astronomical quests, predating modern science by millennia. Ancient Greek cosmology placed Earth at the center of the universe, with celestial spheres rotating around our world in perfect circles. This geocentric model satisfied both observation and philosophy. The heavens appeared to rotate around us, and surely humanity's home must occupy the privileged central position. Ptolemy formalized the system in the 2nd century CE with his complex epicycles and deferents, creating a mathematical framework that could predict planetary positions with remarkable accuracy, despite being fundamentally wrong about the universe's structure. The Copernican revolution of the 16th century displaced Earth from the center, relocating the cosmic focus to the Sun. This heliocentric model placed our star at the universe's heart, with planets orbiting in circular paths around the solar furnace that provided light and warmth. The shift from geocentrism to heliocentrism represented more than astronomical progress. It constituted a philosophical upheaval that demoted humanity from cosmic centrality to planetary insignificance. If Earth wasn't the center, then humans weren't the reason for creation. The cosmos existed independently of our presence, operating according to mathematical laws rather than divine purpose centered on human salvation. But even Copernicus maintained the assumption that somewhere a center existed. The sun might not orbit Earth, but surely the sun itself occupied some special cosmic position, some location more fundamental than others. This assumption persisted for centuries, surviving the realization that the sun was merely one star among billions, that the Milky Way was merely one galaxy among billions, that even our galaxy cluster was merely one structure among countless others, distributed across billions of light years. The development of general relativity in 1915 by Albert Einstein introduced a mathematical framework that would ultimately demolish the concept of cosmic centrality entirely. Einstein's field equations describe how mass and energy curve space-time, creating what we experience as gravity. In Einstein's universe, space is not a fixed stage on which events occur, but a dynamic entity that responds to matter and energy, warping and flexing according to the distribution of mass. This curvature creates the illusion of attractive forces between objects. But at a fundamental level, gravity is geometry, the tendency of objects to follow the curved contours of space-time itself. The immediate consequence of general relativity for cosmology emerged through solutions to Einstein's field equations that describe the universe as a whole. These cosmological solutions revealed something deeply counterintuitive. The universe could be finite in size, yet have no edge, no boundary, no center. The mathematical possibility existed for space to curve back on itself, like the surface of a sphere, creating a cosmos that was bounded but centerless, limited in extent, yet without any privileged location. Alexander Friedmann discovered these cosmological solutions in 1922, showing that Einstein's equations permitted universes that expanded or contracted over time. Georges Lemaitre independently derived similar solutions in 1927, recognizing that an expanding universe implied the cosmos must have been smaller in the past, denser, hotter, ultimately compressed to a singular point of infinite density at some finite time in the past. This was the origin of what we now call the Big Bang theory, though Lemaitre himself called it the hypothesis of the primeval atom. The most disturbing aspect of Friedmann-Lemaitre cosmology is that it describes the Big Bang as occurring everywhere simultaneously, not at a specific point in space. This represents a conceptual leap so difficult that even professional cosmologists sometimes struggle to articulate it clearly. We imagine the Big Bang as an explosion emanating from a central point, like a bomb detonating and hurling fragments outward into surrounding empty space. This visualization is completely wrong. The Big Bang was not an explosion in space, but an expansion of space itself. Every point in the current universe corresponds to a point that existed in the primordial universe. There is no external vantage point from which to observe the expansion, no outside perspective from which one could identify a center. Edwin Hubble's observations in 1929 provided empirical confirmation of cosmic expansion through measurements of galaxy redshifts. Hubble discovered that more distant galaxies show larger redshifts, with the recession velocity proportional to distance, a relationship now known as Hubble's law. This proportionality is exactly what would be expected in a uniformly expanding universe with no center. If the universe expanded from a specific point, galaxies in one direction would show different recession patterns than galaxies in other directions. Instead, Hubble found that expansion looks identical in all directions, suggesting that every location is equivalent, every point is expanding away from every other point, at rates determined only by their separation distance. The cosmic microwave background discovered accidentally by Arno Penzias and Robert Wilson in 1964 provided the most compelling evidence for the Big Bang, and simultaneously the most precise demonstration that the universe has no center. This microwave radiation fills all of space with a nearly perfect blackbody spectrum, corresponding to a temperature of 2.725 Kelvin. The radiation represents the afterglow of the Big Bang itself, photons that have been traveling through space for 13.8 billion years, cooling as the universe expanded until they now appear as microwave radiation coming from all directions with almost perfect uniformity. The temperature uniformity of the cosmic microwave background is extraordinary, varying by only about 1 part in 100,000 across the entire sky. This uniformity demonstrates that the early universe was nearly perfectly homogeneous on large scales. If the Big Bang had occurred at a specific location, we would expect to see temperature variations, corresponding to our position relative to that center. Regions closer to the center would show different temperatures than regions farther away. Instead, the microwave background looks essentially identical in all directions, consistent with a centerless expansion where every location experienced the same initial conditions. However, the cosmic microwave background does show a subtle directional asymmetry called the dipole anisotropy. One hemisphere of the sky shows radiation slightly blue-shifted, while the opposite hemisphere shows radiation slightly red-shifted, with the temperature difference reaching about 3.3 millikelvin. This dipole pattern results from the motion of our solar system relative to the cosmic rest frame defined by the microwave background. We are moving at approximately 370 kilometers per second toward a point in the constellation Leo, creating a Doppler shift that blue shifts radiation in our direction of motion and red shifts radiation behind us. Some researchers initially interpreted this dipole as potential evidence for cosmic centrality. Perhaps our motion indicated flow toward or away from some special location. But detailed analysis reveals the dipole as simply the result of our local motion, not evidence for cosmic structure. When the dipole component is removed, the remaining temperature variations show no preferred direction, no gradient pointing toward any cosmic center. And the universe looks the same in all directions once our local motion is accounted for, exactly as expected in a centerless cosmos. The James Webb Space Telescope was designed to probe deeper into cosmic history than any previous instrument, to detect galaxies so distant that their light has been traveling toward us for more than 13 billion years. By observing these ancient galaxies, astronomers hope to map the distribution of matter in the early universe, to determine whether any large-scale asymmetries or preferred directions existed that might indicate cosmic centrality. If the universe expanded from a specific point, the oldest detectable galaxies should show clustering patterns or density gradients pointing back toward that origin point. The first deep field images from JWST, released in July 2022, showed galaxies in every direction at redshifts exceeding Z=10, corresponding to cosmic ages less than 500 million years after the Big Bang. These galaxies appear distributed uniformly across the sky with no evidence of directional preference. Follow-up spectroscopic observations confirmed redshifts for thousands of high-Z galaxies, creating three-dimensional maps of cosmic structure extending back to when the universe was less than 4% of its current age. The maps show no evidence of any cosmic center. Galaxies at these extreme distances exhibit the same statistical distribution patterns regardless of which direction we observe. The galaxy distribution at high redshift reveals something even more disturbing than simple uniformity. Statistical analysis of galaxy clustering shows that the universe is homogeneous and isotropic on scales, exceeding 300 million light-years. Homogeneity means the density of matter is the same at different locations, on average. Isotropy means the universe looks the same in different directions. These properties are precisely what would be expected in a centerless universe, and they are inconsistent with expansion from a localized origin point. The mathematical framework of the cosmological principle formalizes these observations into a foundational assumption of modern cosmology. The universe is homogeneous and isotropic on sufficiently large scales. This principle asserts that there are no special locations in the cosmos, no privileged observation points from which the universe appears fundamentally different. Every observer, regardless of their position, should see essentially the same large-scale structure, the same galaxy distribution, the same expansion rate, the same cosmic microwave background. This universality of perspective is incompatible with the existence of a cosmic center, which would by definition be a special location from which the universe would appear different than from other positions. But here's where the situation becomes truly bizarre. The cosmological principle is not derived from deeper physical laws, but assumed as a starting point for cosmological models. We assume the universe is homogeneous and isotropic because observations appear consistent with this assumption, and because without it, cosmology becomes mathematically intractable. However, the assumption cannot be proven conclusively because we can only observe the universe from one location, our position in space and time. We see the cosmos from Earth's vantage point in the early 21st century and must infer the view from other locations through indirect evidence and mathematical modeling. This creates a subtle epistemological problem that haunts cosmology. Could the universe only appear centerless from our particular observation point, while actually possessing large-scale structure that would become apparent from other vantage points? Could we be located at or near some special position that coincidentally makes the cosmos appear uniform when viewed from here? This possibility, while seeming to violate Copernican principles about humanity's cosmic insignificance, cannot be completely ruled out through observation alone. No, the anthropic principle offers one resolution to this problem, suggesting that observers will necessarily find themselves in regions compatible with their existence, regardless of whether those regions are typical of the universe as a whole. If the universe contains both typical regions, perhaps with strong asymmetries and preferred directions, and atypical regions, perhaps more uniform and isotropic, intelligent observers will only emerge in regions where conditions permit the formation of stars, planets, and life. These habitable regions might be statistically unusual, creating selection bias, where our observations reflect not the universe's typical state, but the exceptional conditions required for observation to occur at all. The James Webb Space Telescope cannot resolve these philosophical conundrums, but it can provide increasingly precise measurements that constrain the possibilities. By mapping galaxy distributions to unprecedented distances and measuring cosmic expansion with improved accuracy, JWST tests whether observations remain consistent with the centerless universe predicted by standard cosmology, or whether subtle deviations emerge, suggesting hidden cosmic structure. One of JWST's primary missions involves measuring the Hubble constant, the rate at which the universe expands, with unprecedented precision. Different measurement methods have yielded disturbingly inconsistent values, creating what cosmologists call the Hubble tension. Measurements based on the cosmic microwave background and early universe physics yield a Hubble constant of approximately 67 kilometers per second per megaparsec. Measurements based on nearby supernovae and Cepheid variable stars yield a value near 73 kilometers per second per megaparsec. This 9% discrepancy exceeds measurement uncertainties and suggests either systematic errors in one or both methods, or more disturbingly, the possibility that the expansion rate varies with direction or cosmic epoch in ways not predicted by standard cosmology. If the Hubble constant varies directionally, this would indicate cosmic anisotropy, different expansion rates in different directions. Such anisotropy would be inconsistent with a centerless universe and might indicate that we observe from a special location or that the cosmological principle fails on the largest observable scales. JWST observations of distant supernovae and other standard candles will test whether the Hubble tension reflects true cosmic anisotropy or merely systematic measurement errors that will be resolved with better data. The preliminary JWST measurements released through 2024 show no evidence for directional variation in cosmic expansion. Measurements of the Hubble constant using JWST observed Cepheids and supernovae in different sky directions yield statistically indistinguishable values, supporting isotropy. However, the measurements do confirm the higher Hubble constant value near 73, deepening rather than resolving the Hubble tension. The consistency across directions, while maintaining the discrepancy with early universe measurements, suggests that the tension arises not from our spatial location, but from something more fundamental in cosmic evolution, perhaps unaccounted physics in the early universe, or systematic errors in how we model cosmic expansion across different epochs. The discovery of galaxies at redshifts exceeding Z equals 13 by JWST created its own cosmological tension. Standard models predict that galaxy formation should be suppressed at such early cosmic times because the universe was still relatively smooth and homogeneous. Gravity needs time to amplify small density perturbations into the collapsed structures that become galaxies. Yet JWST detected luminous, apparently massive galaxies existing merely 300 to 400 million years after the Big Bang, far earlier than models predicted such structures should exist. These unexpectedly early galaxies don't indicate cosmic centrality, but they do suggest our models of structure formation may be incomplete. If galaxies formed more efficiently in the early universe than current theory predicts, this might reflect previously unknown physics governing how matter collapsed into the first stars and galaxies. Alternatively, some of these high redshift candidates may be misidentified due to unusual spectral properties that mimic the signatures of extreme distance. Follow-up spectroscopy by JWST is resolving which candidates represent genuine early galaxies versus nearby interlopers, gradually clarifying whether the early galaxy excess represents a real tension requiring new physics or an artifact of incomplete observations. The large-scale structure of the universe mapped by galaxy surveys reveals a cosmic web of filaments, sheets, and voids extending across billions of light years. Galaxies cluster along dense filaments, forming a web-like pattern with enormous void regions containing few galaxies. This structure emerged from tiny density fluctuations in the early universe that were amplified by gravity over billions of years, creating the patterns we observe today. The cosmic web appears statistically uniform when averaged over sufficiently large volumes. Different regions show similar statistical properties, with no evidence that structure is denser or more prominent in any particular cosmic direction. Statistical analysis of large-scale structure through correlation functions and power spectra quantifies how galaxy clustering depends on scale. These analyses show that the universe transitions from highly clustered on small scales within individual galaxy clusters to nearly uniform on scales exceeding 300 million light-years. This transition defines what cosmologists call the homogeneity scale, the distance above which the universe can be treated as approximately uniform. The existence of such a scale is predicted by centerless cosmological models and would be difficult to explain if the universe expanded from a localized origin. The baryon acoustic oscillations, imprinted in galaxy distribution patterns, provide one of cosmology's most powerful standard rulers for measuring cosmic distances and expansion history. And then these oscillations originated as sound waves propagating through the early universe's plasma, creating a characteristic length scale of approximately 500 million light-years that appears as a subtle clustering preference in galaxy distributions. By measuring how this characteristic scale changes with redshift, astronomers can precisely track how the universe has expanded over cosmic history. JWST observations of high redshift galaxy clustering will extend these measurements to earlier cosmic epochs than previously accessible, testing whether expansion history remains consistent with centerless models. The cosmic acceleration discovered in 1998 through supernova observations revealed that the universe's expansion is speeding up rather than slowing down, as would be expected from gravitational attraction between galaxies. This acceleration is attributed to dark energy, a mysterious component filling space with negative pressure that drives accelerating expansion. The nature of dark energy remains unknown, but its existence fundamentally affects cosmic structure. Dark energy doesn't cluster like matter, but instead remains uniformly distributed, making its contribution to cosmic expansion truly the same at every location. This perfect uniformity makes dark energy the ultimate centerless component, a cosmic background that exists equally everywhere, treating all locations identically. The possibility that dark energy varies with position or direction has been seriously considered and tested. If dark energy had directional dependence, creating stronger acceleration in some directions than others, this would constitute evidence for cosmic anisotropy and potentially indicate our observation from a special location. Multiple studies using different data sets have searched for directional variation in dark energy strength, finding no statistically significant evidence for anisotropy. JWST observations of distant supernovae will provide additional tests, potentially detecting subtle directional variations that previous studies lacked the sensitivity to measure. The quantum vacuum fluctuations that generated the primordial density, perturbations that seeded all cosmic structure, represent perhaps the most profound connection between the very small and the very large in physics. During cosmic inflation, a period of exponentially rapid expansion in the first fraction of a second after the Big Bang, quantum uncertainty in fields permeating space created random fluctuations in energy density. These fluctuations were stretched to astronomical scales by inflation, imprinting patterns that eventually became the galaxies, clusters, and cosmic web we observe today. The critical property of quantum fluctuations is that they are statistically isotropic. They have no preferred direction, no built-in asymmetry that would create cosmic structure preferentially oriented in specific directions. This isotropy at the quantum level propagates through inflation and subsequent cosmic evolution to produce the observed large-scale isotropy of galaxy distributions. The fact that quantum mechanics produces isotropic fluctuations provides a deep physical reason why the universe should be centerless. The fundamental randomness that seeded all structure was itself directionless, creating structure that statistically looks the same from all vantage points. However, detailed analysis of cosmic microwave background fluctuations has revealed subtle anomalies that challenge the assumption of perfect isotropy. The quadrupole and octupole moments, components describing the largest scale temperature variations, show unexpected alignment with each other and, more disturbingly, with the ecliptic plane of the solar system. This axis of evil, as some cosmologists dubbed it, suggests either profound cosmic anisotropy connecting early universe physics to our local solar system orientation, or more prosaically, key contamination of the data by foreground emissions from the solar system or galaxy that haven't been perfectly removed. Multiple analyses using different microwave background datasets and contamination removal techniques have been unable to definitively resolve whether the axis of evil represents genuine cosmic anisotropy or systematic contamination. The statistical significance hovers at the 2 to 3 sigma level, suggestive but not conclusive. If real, this alignment would indicate either that the cosmological principle fails on the largest observable scales, or that we occupy a special location where local structure happens to align with cosmic structure through extraordinary coincidence. Most cosmologists favor systematic contamination as the explanation, but the possibility of genuine anisotropy cannot be completely eliminated with current data. The shape of the universe, its global topology, fundamentally affects whether a center can meaningfully exist. General relativity permits different global geometries for the universe, each with different implications for centrality. A flat universe extends infinitely in all directions and has no center, just as an infinite plane has no center. Every point is equivalent, with no location distinguished as central. A positively curved universe curves back on itself like the surface of a sphere and is finite but unbounded. It has no center, just as the surface of a sphere has no center. Though the sphere does have a center as a three-dimensional object embedded in a higher dimensional space that the universe itself is not embedded in. And measurements of cosmic microwave background anisotropy have determined the universe's spatial curvature with extraordinary precision. The data indicate that space is flat to within measurement uncertainties of approximately 0.4%. The universe's curvature parameter, omega k, is measured to be minus 0.001 plus or minus 0.002. This near-perfect flatness means that on cosmic scales, space follows Euclidean geometry, where parallel lines never meet, and the angles of triangles sum to 180 degrees. A flat universe can be either infinite in extent or finite with periodic boundary conditions, like the surface of a three-dimensional torus. But either way, it has no center in the conventional sense. The extraordinary flatness of the universe represents one of cosmology's deepest mysteries. According to standard Big Bang models, any initial deviation from exact flatness should be amplified over time by cosmic expansion. A slightly positively curved universe should become increasingly curved, while a slightly negatively curved universe should become increasingly hyperbolic. The fact that the universe remains flat to high precision after 13.8 billion years of expansion suggests either that initial conditions were fine-tuned to extraordinary precision, with flatness accurate to 1 part in 10 to the power of 60 at the Planck time, or that some mechanism in the early universe drove the geometry toward flatness. Cosmic inflation provides a natural mechanism for flattening spatial curvature through exponential expansion. During inflation, the universe expanded by a factor of at least 10 to the power of 26, and stretching any initial curvature to such enormous scales that the observable universe appears flat, just as the surface of a balloon appears flat when inflated to sufficiently large size. This expansion doesn't create a center. It simply stretches any pre-existing curvature to scales far larger than we can observe, making our observable patch appear geometrically flat while leaving the global topology undetermined. The multiverse hypothesis, emerging naturally from many versions of inflationary cosmology, extends the centerless universe concept to its ultimate extreme. If inflation occurred in our region of space, it likely occurred in countless other regions as well, creating a vast or possibly infinite ensemble of causally disconnected universes, bubbles of space that underwent inflation and Big Bang expansion independently. Each bubble universe would have its own physical properties, vacuum states, and cosmological parameters, with different regions potentially having different physical laws. In the multiverse framework, asking for the center of the universe becomes even more meaningless than in standard cosmology. Not only does our observable universe have no center, but our entire universe, everything that could in principle be observed if we waited long enough for light to arrive, is merely one bubble among countless others in a vaster multiverse structure. This multiverse itself likely has no center, existing as an ever-inflating substrate, generating new bubble universes throughout eternity. The hierarchy of scales without centers extends upward without limit, from our cosmic neighborhood to our Hubble volume to our bubble universe to the infinite multiverse. The philosophical implications of a centerless universe extend far beyond cosmology into questions about meaning, purpose, and humanity's cosmic significance. Throughout history, cultures located themselves at cosmically central positions, with creation myths and religious cosmologies placing human civilization at the universe's heart. The progressive displacement from centrality, from geocentrism to heliocentrism, to the realization that our galaxy is unremarkable, our cluster is ordinary, our cosmic neighborhood is typical, has been psychologically disorienting. Yet, the centerless universe need not imply meaninglessness or insignificance, and the fact that every location is equivalent doesn't diminish any particular location. It elevates all of them equally. In a centerless cosmos, our position is just as valid as any other, our perspective just as legitimate. The universe doesn't privilege any location, which means it doesn't discriminate against any location either. We are not at the center, but we are not at the periphery either, because there is no periphery to be at. We simply are wherever we happen to find ourselves, observing a cosmos that looks fundamentally the same from all vantage points. The mathematical elegance of a centerless universe appeals to physicists who seek explanatory parsimony and universal principles. A cosmos with a center would require explaining why that center exists, what physical laws operate differently there, why the universe expanded from that particular location rather than somewhere else. These questions multiply explanatory burdens, requiring additional assumptions and special conditions. A centerless universe requires no such explanations. It is the simplest possibility, consistent with general relativity and the cosmological principle, requiring the minimum number of assumptions about cosmic structure. The observational program of the James Webb Space Telescope will continue testing cosmic homogeneity and isotropy through increasingly precise measurements of galaxy distributions, expansion rates, and large-scale structure across cosmic history. If subtle deviations from uniformity emerge in the data, if directional preferences appear in cosmic expansion or structure formation, if evidence accumulates that our position is somehow special rather than typical, the centerless universe paradigm will face serious challenges requiring either modification of cosmological models or introduction of new physics. But current data, including all JWST observations released through 2024, show no evidence for cosmic centrality. Every measurement confirms that the universe looks the same in all directions on sufficiently large scales, that expansion proceeds uniformly regardless of direction, that structure formation follows the same statistical patterns in all regions. The preponderance of evidence supports the disturbing conclusion that the universe has no center, that the Big Bang occurred everywhere simultaneously, and that our search for cosmic centrality is conceptually misguided, asking a question that seems meaningful but actually rests on false assumptions about the nature of space and time. The failure of the James Webb Space Telescope to find the center of the universe thus represents not a technological limitation, but a fundamental insight into cosmic structure. We haven't failed to find the center because our instruments lack sufficient sensitivity or because we haven't searched thoroughly enough. We've failed to find it because it doesn't exist, not as an undiscovered location awaiting detection, but as a meaningless concept like the edge of an infinite plane or the direction north of the North Pole. This realization forces us to reconsider our intuitions about space, challenging the deeply ingrained notion that everything must be somewhere, that every collection of objects must have a center of mass, that every expansion must have a point of origin. The universe defies these intuitions, operating according to principles that violate our everyday experience, while remaining perfectly consistent with the mathematical laws of physics. We stand at a crossroads in our cosmic understanding, able to observe the universe across 13.8 billion years of history and billions of light years of space, yet unable to answer one of the simplest questions a child might ask: where is the middle of everything? The question has no answer, not because we lack knowledge, but because the question itself is malformed, based on assumptions that don't apply to the cosmos we actually inhabit. The universe is watching how we respond to this centerlessness, testing whether we can abandon comfortable illusions in favor of strange truths. The centerless cosmos challenges our narcissism and humbles our pretensions, removing the possibility that we occupy any cosmically privileged position. But it also liberates us from the burden of centrality, freeing us to explore a universe where every location is equally valid and equally significant. The journey through cosmology's deepest findings reveals that the universe is stranger, more subtle, and more elegant than our evolved intuitions about space and position can easily comprehend. The failure to find the center is not a disappointment, but a revelation about the fundamental nature of reality, a reality that operates according to mathematical principles that transcend human intuition while remaining accessible to human reason. The final message is this: the James Webb Space Telescope hasn't failed at all. It has succeeded brilliantly in confirming what cosmological theory predicted, that the universe is a centerless manifold of space-time, homogeneous and isotropic on large scales, expanding uniformly in all directions from all locations simultaneously. This success feels like failure only if we cling to outdated intuitions about cosmic structure. Once we release those intuitions and accept what the data reveals, we find ourselves inhabiting a cosmos far more remarkable than any centered universe could be. A cosmos where we are simultaneously nowhere special and everywhere significant. Observers witnessing infinity from one among countless equivalent vantage points scattered across the endless expanse of space and time.